So the LeetCode problem we are going to do is called last stone weight. Now, in my opinion, this is one of the most awesome problem I've seen. We can see that this one is an easy problem and also a very well-liked problem. The problem statement is that we are given an array integer of stones that defines the weight of every single stone that is currently present. Okay. Now we are playing a game with these stones. Now during the each turn, we choose the heaviest two stones. So this is the important part. We choose the heaviest two stones and then smash them together. Now the question is, there can be two possibilities. One possibility is that either for two stones X and Y, either both are of same weight or both are of different weight, which means one is heavier than the other. If both are of same weight, then both stones get destroyed. Okay, because we are smashing them together, both stones get destroyed. If that is not the case, and if we realize that one stone is heavier than the other, then the stone with lesser weight gets completely destroyed, and the stone with higher weight has a new weight that is like a y minus x. So whatever the difference between weight is between two weights, and then we are going to keep on repeatedly going to do the same process until the end of the game, where there is only one single stone left, and then we are going to see that what is the weight of that particular stone, and that's why the name is last stone weight. Now let's try to understand this with an example so it would make more sense. Currently we are given an array where every single value represents the weight of stones at that particular position. What are we being told? That we need to find the two heaviest stone during every single iteration. So currently two heaviest stones are going to be 8 and 7. So currently 8 and 7 are not equal to each other, which means when these two stones get smashed, this 7 is going to completely be destroyed, and this stone 8 is actually going to be only of size 1, because we will have to do 8 minus 7. Okay, following this particular condition. So once again, if we do that, currently we have this 7 gets completely destroyed, and we have this element number 8 that is now being turned into element number or stone weight size 1. So now the new array we have is values 2, 4, 1, 1 and 1 and 3. Once again, we are going to repeat the same process. So find the two heaviest stones that are 4 and 3. Once again, both are not same. So once again, if 4 and 3 gets collided, we are going to left with one stone that weighs 1 kilogram, and this stone number 3 is going to get destroyed. So the new array we are going to get is going to look like this, where the values are 2, 1, 1, 1, 1. Okay, so once again in this case, now this 2 and 1 are both are the stones, so they both are going to be crashed against each other. So if we do that, once again this stone will get completely destroyed. This one only becomes of weight 1. So new value is going to be 1 amongst these two, and then these 3 ones we already had. Okay, so now once again we are going to repeat the same process. Now two heavy stones are both contains the same weight. If the weight is same, both gets destroyed. So in the next iteration we are only left with two stones, 1 and 1. And once again, if we try to smash these two stones together, both will also get destroyed. So we will not have any stones left in this case, so we will need to return 0. Now let's say in the same condition, let's take one more example where we try to have some weight inside the stone. So let's say the values are, now in this case currently the two heavy stones are this 8 and 6. If both gets smashed, then we will have values with 2, 3 and 4. 6 will get destroyed. So once again the two heavy stones are 3 and 4. So once again, if both get smashed, then this 3 is going to be destroyed, and we are going to be left with values 2 and 1. If these two get smashed together, then this 1 is going to get destroyed, and last stone will only be left with size 1, and this is what we need to return as the answer. So basically this is what the problem statement is asking us to solve. The brute force approach is actually going to be quite straightforward, where at every single iteration we will first have to find the two heaviest stones. Once we find the two heaviest stones, then doing all the remaining work is not that much complicated. Then we can simply find the difference between them, and then once again create a new array, and then once again try to repeat the same process until we are only left with just one stone or no stones at all. So brute force approach would yield us the correct result, but the issue is For every single time, if we have to find the two heaviest stones for each of the remaining array, basically we are going to be doing big of n square work just to find the two heaviest stones. And once we do that, solving this problem is very simple and very easy to do. So the question we will have to focus on is that how can we improve upon the scenario where finding the two heaviest stone becomes very convenient for us at every single iteration. And for that, the idea is whatever the given input array is, we will actually try to create a priority queue or a heap where we are going to store all the values, and we are going to set up this heap to be of max heap type. So max heap means that whenever you try to add the values inside the heap, it is going to store the maximum element first and then smaller elements later, which means it is going to store all the values inside the descending order. Okay, this is the whole concept of max heap. So that's what we are going to use in this problem. And let me quickly show you that using max heap, this problem becomes really easy to solve. The idea is that first, currently we are simply going to iterate over every single values and start putting them one by one inside the max heap. If we do that, we will get a sort of I would say a value that is sorted in decreasing order. So very first element is going to be value number 7, and then we will have value number 6, and once again then we will have all the subsequent values in the same decreasing order. And this is the input we currently have. So once after finding this input, in order to find our x and y values, we simply need to poll these two values in. And after polling these two values, all we need to do is find that if they are of same size, then destroy both of them and move forward. If they are not of the same size, find that what is the delta between them, and whatever the difference is, try to put that back inside the max heap. Keep on repeating the same process until we are only left with just one element. And let's try to see the solution I'm proposing in action. So once again, in this case, currently this is our max heap, and currently these are the two largest elements, 7 and 6. We will try to pop them out, and we find that the difference is going to be 1. Okay, so currently this 7 and 6 has been popped out, and we have element number 1 that needs to be added. So in order to add element number 1, it will be added in the back side of the heap. So we will I will not draw a new heap. I will just keep on adding 1 values. Okay, and these are just empty shells, so don't just ignore them. Now once again, during the next iteration, we are going to find the two heaviest elements, that are 4 and 3. Once again, the difference is going to be 1. So once again, now we no longer have values 4 and 3 inside the heap, and we are just going to add one more element, 1, at the end of the heap. Next two heavy elements are 2 and 2. So because both are same, so we are simply going to ignore them and not add any other values. Now the two heavy elements inside the given heap are 1 and 1. Once again, both are same, so we are going to delete both of them and don't do anything. And lastly, there is only going to be one stone left, that is going to be of size 1, and this is what we need to return as the answer. So you realize that after storing all of this information inside a heap, that is a self-balancing data structure that automatically sorts itself with new elements being added, how easy this problem becomes. So once we implement the heap, this problem is very simple, and we know that insertion inside the heap takes log n time, and we will have to do it for n given input. So it's going to take n log n to store all the values and complete this problem. So this is going to be the time complexity. If we see space complexity, that is going to be big O of n, because we will have to create a new heap to store all of these values. So there is no other way to move around that, but still this is a very good time and space complexity. Now let's try to quickly see the coding solution for this one. Okay, so first of all, we are going to initialize our max heap, and this is how we actually initialize it using the priority queue. And in the comparator class, we are mentioning that only the maximum element has to be at the beginning of the heap. Then we are going to add all the values inside our max heap, and then we are going to continuously remove and smash the two heaviest objects until we are only left with just one element. And for that, we find our y as the very first element inside the heap, we find our x as the second element inside the heap. We simply have a condition that if x is not equal to y, then we are going to add the element that is the difference of weight between y and x elements back inside the heap, and keep on repeating the same process while the size of the heap is greater than 1. and the moment we reach to the end, we are simply going to check that if the heap is empty, we are going to return 0. If the heap is not empty, we are going to poll the last remaining element inside the heap as the answer, and that is going to be the heavy last remaining stone weight of our original input of stones that we were given. So now let's try to run the code. Seems like our solution is working as expected. Let's submit this code. And our code runs 98% faster than all the other solutions. That in itself suggests that we are doing something really good and really right. So once again, this coding solution is present inside our GitHub repository. You can go and check it out from there. Thank you.